demand. So the optimal choice, so that x1 and x2 star of goods 1 and 2, I mean, up to n if we had n different types of goods, at some set of prices, and income, is called the demanded bundle. Is the demanded bundle. Now, when prices or income change, that demanded bundle can change. When prices or income change, this optimal choice, this x1 and x2 star, are likely to change. So the demanded bundle is going to change. I don't know if I need commas there. When prices or income change, in general, it's not always the case, but in general, the optimal choice will change. Will also change. So our demanded or demand functions for these two goods, x, the demand for good 1, is going to be a function of the price of good 1, the price of good 2, and income. And the same thing for the amount of good 2. It's a function of the price of good 1, the price of good 2, and income. And different preferences will result in different demand functions. So we're going to explore some different preferences that we saw in previous chapters and think about what their demand functions look like. So perfect substitutes and perfect complements. And then we'll kind of move on and kind of talk, we're going to apply some calculus to this and kind of talk about implications for taxes and things like that. Substitutes. And we're going to assume that there's this one-for-one exchange, like with the black and blue pens. We're not going to have 2 black pens for 1 blue pen, et cetera, et cetera. So let's assume it's a one-for-one exchange. So we can have 3 possible cases. The first is that the price of good 2 is greater than the price of good 1. We're willing to exchange them 1 for 1, but the price of good 2 is greater than the price of good 1. Well, we're going to spend our whole budget on good 1 because it's cheaper and we like it just as much as good 2. And kind of visually what's happening here is the slope of the budget constraint is flatter than the slope of the indifference curves. Remember, if it's a 1-for-1, the slope of the budget constraint is, the slope of the indifference curve is -1. And here, if P2 is greater than P1, then the slope, remember, which is negative P1 over P2 is less than 1. So you have like a flatter slope, which means that we're going to get a corner solution and we're only going to buy product or commodity 1. The second case would be if the prices were equal. Well, this is a bit, I don't know if it's more complicated or not, but we could have like a continuum of different optimal bundles for this consumer, because if the prices are the same and the value the same, then as long as they're spending their whole budget, that's good enough. They're gonna be maximizing their utility and they're in the highest indifference curve possible. So any combination that satisfies the budget constraint, sorry, is optimal. So there's no kind of unique solution in that situation. And finally, we could have the opposite of here, this first case where P2 is actually less than P1. Well, now we're just going to be spending all of our money on good 2 because, again, we're willing to exchange them 1 for 1, and now commodity 2 is just cheaper than commodity 1. So we're just going to buy all commodity 1 because we like it just as much. So only purchase good 2. And so if we want to kind of write out what this means maybe mathematically, then our demand for X, or I'll put X1 here, is M over P1 if P1 is less than P2. We're going to spend, spending all of our money. Remember, M is our budget, P1 is the price of good 1. This is how much X1 we can afford if we spend our entire budget. So if P1 is less than P2, we're going to spend our entire budget on good 1. This middle case here could be any combination between 0 and M over P1. And finally, 0 in the last case. Hopefully this is fitting on the screen, I guess I'll have to check afterwards. So this is if that's true, this is if P1 equals P2, the second one, hopefully that fits on the screen, and this last one is if P1 is greater than P2. So this is like what our demand function looks like for these perfect substitutes. If we wanted to draw it out, we can draw like the first case out maybe. Here's X2 and here's X1. Let's say these are our indifference curves here. They have a slope of -1. If we're willing to exchange 1 for 1. And in this first case where P1 is less than P2, what's happening is that our budget line is flatter. And so we're at this point here where X1 star equals M over P1 and X2 star equals 0. That's this kind of this first situation here. The second situation is that basically these lines are kind of on top of each other. That the budget constraint and the indifference curve are basically the same line. And the third case is if, instead of having this budget line being flatter than these indifference curve, it's steeper. And so we kind of connect on this axis and this y-axis. The intercept is we're going to have only good X2. Okay, so that's how the demand functions work for perfect substitutes. Now let's move on to perfect complements and then neutrals and bads and so on and so forth. And again, we're going to look at the simplest case possible. We want the equal amount of both goods. So remember with left and right shoes, for example, we want equal amounts of each of the shoes. We're going to make that assumption. We come up with our demand function here. Now, if it was a different, with our tea and coffee example, we want 2 teaspoons or 2 tablespoons of sugar in your tea per cup of tea, that'd be slightly different. But hopefully you can think of how to generalize the simplest cases, right? So we're going to look at the simplest case. It's going to be, I think, pretty straightforward to kind of generalize in your head. We'll want equal amounts of both goods. Oops, no either. Sorry, my writing's bad this week. And so if that's true, we have our budget line, P1x1 plus P2x2 equals M. But we know x1, equals x2 here, right? We have the same numbers, and so we can just call that x. And so essentially, like, phi 1 of x is costing us p1 plus p2, right? So if this is true, then we can kind of rewrite our budget constraint. That's p1x plus p2x equals m, which means x equals m over p1 plus p2. Just, we can common factor the x out and divide both sides by p1 plus p2. So essentially, what we're thinking of here, essentially a single good with a price of p1 plus p2. And how to think about this case, and hopefully it will be large enough down here, amount of good 1, amount of good 2, we have these indifference curves that were these right angles, where that kind of kink is at 1, 1, 2, 2, 3, 3, or whatever the equal number on the x and y axis, like these kinks are along the x equals y kind of locus that's coming out of the origin here. And so essentially then we have, this is the amount of x1, and this is the amount of x2. So that's how perfect complements work.